Hello everyone, welcome back to Networks class. So last time what we did was we reviewed big O notation and then we reviewed data structures, or at least a few basic data structures that we're going to use in class. And the plan for today is to talk about describing graphs mathematically and storing graphs in the computer. So let's get started. So before we get into describing graphs mathematically, let's review some basics about mathematical collections. So in particular, mathematical collections have two important properties, which is are they ordered and do they allow repetition? So the most common mathematical collection that you're probably all familiar with is a set. So a set is not ordered and it does not allow repetition. And what I mean by this is the following, that if we have something like the set AB, that's exactly equal to the set BC or BA. So in other words, the order here didn't matter. Just because A came first and then B, that doesn't matter. I could just write it as B comes first and then A. And also, I'm not allowed to have a set that has the same element repeating twice. So as you might imagine, there's four other possibilities here. So a tuple is ordered and it allows repetition. A multiset is not ordered, but it does allow repetition. And these are really the three we're going to use in class, but just for completeness, let's write the last one, which is a permutation. And that one is indeed ordered and does not allow repetition. So in the history of studying graphs, there were basically two communities that started looking at these problems. And because of that, there turned out to be dual terms. So typically, a graph can also be called a network. And typically, we write it as the following. So G equals VE, where V is a set of vertices or nodes. And usually the size of V we write as n. And E are the edges or arcs of the graph. And typically the size of E we write as m. So let's just draw a couple of example graphs that we can refer back to as we're kind of learning how to talk about graphs. So here's four examples. So example one, it has these three vertices and some edges. Example two has again three vertices and some edges. Example three also has three vertices and some edges. And this is example 4. Okay, so we have these four example graphs, and they'll help us just learn the various terms that we need to discuss graphs. So if we go back here, notice that I said V is a set. And V is always a set. So in particular, if you look at these four examples, the set of vertices for all four of the examples is the same. So in that example, V was just the set A, B, C. Those are the three vertices in all four of the examples. But E, the edges or arcs of the graph, sometimes they're a set, and sometimes not. So let's take a look at these examples. So in examples 1, 2, and 3, the edges are a set because there's no edge repetition. So every edge is different from every other edge. But in example 4, in particular over here, an edge repeats. In particular, this edge from A to B appears twice. And so since that edge appears twice, the group of edges is not a set. So it's a set in examples 1, 2, and 3. And sometimes it's a multiset. So that's in our example 4. And this is such an important distinction that actually this word multi gets promoted to discuss the graph as well. So if E is a multiset, then G is called a multigraph. And this central idea, if an edge repeats, in fact does make it into many, many of the computer programming libraries that people use to do graph computations. So oftentimes there's entirely different data structures for holding graphs versus multigraphs. And you'll see later in the course when we start doing GAMs that GAMs cannot store multigraphs. So let's continue by trying to discuss what kind of collection. So what kind of collection is an individual edge? So what I mean here is not the big set of edges, but just one of these little edges that's inside of the big set of edges. So let's look back here at these examples. So if you look at example 1, here the order really does matter because the edge that starts at A and goes to B is different than the edge that starts at B and goes to A. So in that particular example, order matters. And in example 3, you see that we have an edge that kind of repeats because it starts and ends in the same node. So sometimes edges are directed. And so in our examples here, in examples 1, 3, and 4, the edges are directed. And in that case, E is a tuple, and G is called a directed graph. And sometimes the edges have no direction. So usually people say are undirected. And in that case, G is called a undirected graph. So in our examples here, example 2 is an undirected graph, but examples 1, 3, and 4 are directed graphs. And the final sort of terminology that we need to introduce about individual edges is that if an edge connects a node with itself. So what I mean here is that, for example, this edge here connects the node B with the node B. And so that edge we call a self loop. So the only graph that has a self loop in our examples here is graph number 3. So that really allows us to categorize graphs in 3 different ways. So the major ways of categorizing graphs are the following. Is it a graph or is it a multigraph? Is it directed or is it undirected? And does it have self loops or no self loops? And so let's go back and try to categorize our 4 examples here. So example 1 is a directed graph with no self loops. Example 2 is an undirected graph with no self loops. Example 3 is a directed graph with self loops. And example 4 is a directed multigraph without self loops. So let's me just complete one piece of information here, which is what kind of collection is an individual edge? So if an individual edge is directed, then it's a tuple. And as you might imagine, if E is undirected, then order doesn't matter. And so we say that E is a set or multiset. Of course, the difference between a set and a multiset is if it allows repetition. And so if I had a self loop over here in example 2, then this particular individual edge that I just added here would be a multiset. Because it really just has 2 things in it, B and then B. So that really concludes our description of how to categorize graphs in general. And we also have now a way of describing the graph structure overall. So if somebody comes along and gives you a set of nodes and a set of edges, then you can go off and you can draw the graph, especially if they tell you if the edges are directed or not, you know exactly what that means. But another thing that's going to be useful is how to describe a graph from the point of view of a single node. So let's talk about that. So think about a single node A. And let's talk about all of the edges that happen to be touching the node A. So let's introduce a term for that. So if an edge involves node A, then we say the edge is incident on A. So we're kind of writing all these definitions in English, but you can just as easily write them down in mathematical terms. And what does it mean for an edge to be incident on A? So that means that E is incident on A if E is equal to AX or E is equal to XA for some other node X and V. But the English is just as easy to understand as the math, so let's just stick to the English largely. So let's introduce one more definition to talk about sort of the graph from the point of view of node A. So if edge AB is in the graph, then we say A and B are adjacent. So, and that really makes sense because if you think about it, an edge makes one node be next to each other, and so that's where the word adjacent comes from. The degree of A is the number of edges incident on A. So let's just practice our mathematical notation here one more time. So the way that you can write that is first let's write down all the edges that are incident on A. So I'm looking for edges such that E is equal to XA or E is equal to AX for some X and V. So that's the set of all edges that are incident on A. And the degree of A is just going to be the size of that set. Quite similarly, we might care if the edges are coming into A or going out of A, so we'll define in degree of A is the number of edges going into A, and out degree of A is the number of edges going out of A. So similarly to just talking about the edges that are going into and out of A, we might want to talk about the nodes that are kind of next to A. So we'll define the neighbors of A to be all the nodes adjacent to A. So let's write that down. Mathematically, it would be something like we're looking for nodes X such that XA is an edge or AX is an edge. So the neighbors of A is a set of nodes, and that's what we've written down mathematically over here. And similarly, we might define the predecessors of A, which are all the nodes X such that XA is an edge, and the successors of A, which is all the nodes X such that AX is an edge. So let's maybe go back and see some examples of these definitions in our four examples here. So let me just ask a few questions, which is, let's take a look at this node A. What is its degree? So the degree of A is just the number of edges that are coming into or out of A. It doesn't matter. So its degree is 2. Its in degree, which is the number of edges going into it, is 0. And its out degree is 2. So let's take maybe another example. Let's take a look at this node right there. Its successors are which nodes? There's exactly two of them, A and B. Or rather, B and C are the successors of A here. And the predecessors are just one node, which is just B. So that gives you just an example of applying our definitions to the small graphs that we saw earlier. Okay, so now we have a method of discussing graph structure both on a global scale and from the point of view of an individual node. So let's start thinking about how we might go about storing one of these graphs in a computer. So let's just take a look at a simple example. So here's a small graph. It's going to have these 4 nodes, and let me put down a few edges. So imagine that we want to store this particular graph in a computer. So the two things that we need to store are the two things that we need to describe the graph. So the first thing that we need to store is the nodes. And it turns out that storing the nodes is relatively easy. So the thing that we're going to do to store the nodes is we're going to put them in an array. And an array really provides us with all the things that you might want out of nodes. So in terms of memory usage, the array takes O of n memory to store all the nodes because it's just going to have one little spot of memory for each node. And if somebody comes along and asks me, can you give me all of the data for node 2, I can access the data for node 2 very quickly in O of 1 time just by jumping to the right spot in memory. So nodes turn out to be relatively easy, but let's think about how to store the edges. So an initial kind of try that we might do is maybe store them in an array or a linked list. So let's see how well this particular idea works. So how much memory does this take? Well, I need to have one spot of memory for each edge, so O of m memory in general, regardless if we do it as an array or a linked list. So what about if somebody comes along and wants to see if a particular edge AB is in the graph? So just as an example, maybe somebody comes along and says, is edge 1, 3, is it in this graph over here? So to do that, I basically have to see if 1, 3 is somehow stored in my list of edges or in my array. So in general, if things are not ordered, this takes O of m time because I have to scan through all of the list of edges to see if the one that I'm looking for happens to be in there. But if I have a sorted array, I can do this in O log m time using the binary search trick that we talked about before. And sorting edges is just as easy as sorting numbers. You can just do it based on coordinates or something like that. So that's how long accessing takes. And another very common operation that we're going to want to do is to find the successors of something. So imagine that somebody comes along and asks me, what are all the successors of, say, node 1? And then I would have to answer that the successors of node 1 are node 0 and node 2. So how long would it take us to answer this question? Well, in general, I'd have to search through my whole list of edges again. So to see if there's, and basically just every time that I see an edge that starts at A and ends in some other node, I can add that other node to my list of successors, and then I can answer the question that way. And it does turn out that if you use a sorted array, you can answer this question in log m time. Um, And the reason for this is, let's just do this for the example up here. So a sorted array would look something like this: 0, 1, 1, 0, 1, 2, and then 2, 3. So over here, I've just written down the 4 edges in our little example up there and sorted them. And so if somebody asks for the successors of 1 here, all I have to do is do binary search on this until I get to this very first edge that comes out of 1. And I know that all the other edges that come out of 1 come right afterwards. And so answering the successors question still takes log m time, because we can use binary search to just find the beginning of this list of edges. So that's kind of our first shot for storing the edges, but the reason this is bad is the following. So first of all, access takes too long, and perhaps even more importantly, successors takes too long. So you'll see very shortly that successors really is the central operation that we need to do on a graph to be able to execute our graph algorithms. And so let's try to think of other ways that we can store the edges of a graph that make things faster. So here's another idea for storing the edges of a graph. And the basic idea is from the fact that arrays have fast access. So let me introduce you to what's called the node-node adjacency matrix. So the basic idea of a node-node adjacency matrix is the following. On the rows, I'm going to put the source node. And on the columns, I'm going to put the destination node of a particular edge. So let's just go back to our example here with these 4 vertices and try to write down its adjacency matrix. So the vertices were 0, 1, 2, and 3. 0, 1, 2, and 3. And so the idea is that we're going to place a 1 here if the edge is in the graph, and 0 otherwise. So let's do this. So I need to put a 1 on location 0, 1. So 0, 0 gets a 0. 0, 1 gets a 1. What about 0, 2? 0, 2, there's no edge, and 0, 3, there's no edge. So 0, 2 and 0, 3 are both zeros. If we go back, the only edges that 1 has are to 0 and to 2. And so the next row is going to be 1, 0, 1, 0. And the 2 1s come out of the 2 edges that come out of the node 1. The next row is going to be just 2 has an edge to 3 and no other edges. So we're going to have a 1 over here and all zeros otherwise. And the last row is all zeros because node 3 doesn't have any edges coming out of it. So that's the node-node adjacency matrix of the simple example that we had. So let's ask our 3 questions of this way of storing the graph edges. So how much memory does this take? The answer is O of n squared. So O of n squared because I have n rows and n columns in the matrix. which means that there's n squared entries. And each of those entries has a number in it. Some of them are zeros and some of them are ones, but each of them has a number. And so that's why the memory is O of n squared. So what about accessing? So somebody comes along and asks if edge AB is in the graph. So if somebody comes along and asks me if edge 1, 1 is in this graph, what I would do is very quickly jump to 1, 1 and be able to answer that in O of 1 time. And that's because the matrix here is just stored in a contiguous part of memory. And so when somebody asks me for a 1, 1, I know exactly the place to jump to see if there's a 0 or 1 over there. So this is exactly for the same reason that array access is fast. So what about successors? So somebody comes along and asks me, what are all the successors of node 1? Well, to answer that question, I basically have to scan the appropriate row. So that takes O of n time, and that's because we have to scan the row for node A. So if somebody asks me, what are the successors of node 2, I go to the second row here and see, okay, 0, 0, 0, but there's a 1 in the third column, and so 3 is a successor of node 2. So we got some benefits and some not so good things when we switched from storing the edges in a linked list or array into this adjacency matrix. So a benefit is this access time. So this is significantly faster than what we had before. But a downside is this memory, and another downside is that successors got slower. So it turns out that usually the number of edges in a graph is going to be much, much smaller than n squared. And so this memory over here that we're getting is very expensive. And so a node-node adjacency matrix does take us some part of the way to being faster, but not all the way. So let's try to figure out how we can get back to this nice memory property that we had before, but maybe still keep the fast access times. So the basic idea here is that we're going to use ideas from sparse matrices. So if you look at this adjacency matrix that we created for our example graph, most of that matrix is just made up of entirely zeros. And that's just a lot of space that we're wasting. And so the idea of sparse matrix formats is to not store all the extra zeros, is to just store the locations and values of the non-zero entries. So let's understand how to do that. And really, sparse matrix formats are much more general than just talking about graphs. And so when we introduce them, let's do so with an example that just takes maybe an arbitrary matrix. So here's an arbitrary matrix, 0, 1, 2, 3, 0, 1, 2, 3 for the columns as well. And let's put some data in it. So here's a 0, and it's here's a matrix, and it's sparse because it has so many zeros in it. So the idea for sparse matrix formats is that all we need to store is the location 0, 1 and the value 11. And then for any location that we haven't stored, we can just assume that it's 0. So our first sparse matrix format is going to be called a dictionary of keys. And the idea here is to just store things in a hash table. So let's see how that would work. So a hash table has some keys and values. And the idea is to have the key be 0, 1, and the associated value be 11. So the key here is the location of the non-zero entry, and this is the value of the non-zero entry. So just taking this example matrix that we have at the top of the page and figuring out what the rest of the key value pairs in the hash table would be is something like this. So location 1, 0 has a 12 in it. Location 1, 2 has a 13 in it. Location 2, 3 has a 14 in it. And that's it. That's all the information that we need to store about the sparse matrix at the top. So let's ask our 3 questions, which is how much memory does this dictionary of keys format take? Well, it takes O of m memory, because now all we're doing is we're just storing the non-zero entries. So all the zeros disappeared. What about access? So somebody comes along and says, is edge AB in the graph? Or what's the value of location AB in the sparse matrix? Well, you can answer that in constant time, because you're just going to take this key, you're going to pass it through the hash function, and you're going to see what the associated value is. And our last question is successors. How long does that take to compute? So somebody comes along and says, what are all the successors of node A? Well, you can't do anything other than look through everything that's in the hash table. And so that takes order m time. So all you can do is just look through all of the keys here to find all the keys that start with A and end on something else. And so this dictionary of keys format got us really fast access time. It got us really nice memory, but successors here was too expensive. So that part was not good. So let's conclude lecture here for today. Thanks for listening.